At more than 11,000 meters below the surface, sunlight disappears, radios go silent, and steel can fold like paper. This place, Challenger Deep, is Earth's last hidden frontier, a world fewer humans have entered than the surface of the Moon. What secrets wait in this crushing darkness, and why do we still know so little about it? Your depth gauge climbs past 11,000 meters. The pressure around your vessel now exceeds 1,000 bars, 16,000 pounds per square inch, crushing every surface. Your radio crackles once, then dies. GPS signal vanishes. Even light itself surrenders to the crushing weight of water above. Before we dive deeper into this abyss, hit that subscribe button and let me know in the comments where in the world you're listening from tonight. Your support helps us explore the most fascinating mysteries on Earth. This is Challenger Deep, the deepest known point in our oceans. And here's what's truly unsettling. Despite all our modern technology, despite sending rovers to Mars and telescopes to the edge of the universe, only a few dozen humans have ever witnessed this place firsthand. Fewer people have been to the bottom of our ocean than have walked on the Moon. The Hadal Zone begins at 6,000 meters down, but Challenger Deep plunges to nearly 11,000. Down here, the pressure would instantly crush a human body. Steel implodes like a tin can. Communication systems fail. Navigation becomes impossible. Even our most advanced deep-sea vehicles struggle against forces that seem almost alien in their intensity. What's waiting down there that we still can't reach? What secrets lie beyond the limits of human engineering? And why, after decades of technological advancement, do the deepest places on our own planet still defeat us? The answers might disturb you more than the darkness itself. The ocean doesn't just get deeper, it transforms. Each layer strips away another piece of the world we know until you reach places that might as well exist on an alien planet. At the surface, in the epipelagic zone, sunlight penetrates down to 200 meters. Here, photosynthesis still works. Marine plants can survive. Life thrives in familiar ways, but cross that 200-meter threshold and everything changes. Welcome to the twilight zone. The mesopelagic stretches from 200 to 1,000 meters down. Sunlight fades to nothing. Photosynthesis becomes impossible, yet life persists in ways that defy logic. Bioluminescent creatures create their own light shows in the perpetual dusk. Jellyfish pulse with electric blues. Deep sea fish flash like living constellations. This is where the ocean first shows you that it plays by different rules. Drop another 1,000 meters into the Bath hypelagic, the midnight zone. No sunlight has touched these waters in millions of years. The temperature hovers just above freezing. Currents move with geological slowness. Here, pressure begins its relentless squeeze. 4,000 meters down, you're experiencing pressures that would crush most surface vessels like aluminum cans. But we're still not at the bottom, not even close. The abyssal zone extends from 4,000 to 6,000 meters. Vast underwater plains stretch across seafloor distances larger than continents. The water temperature stabilizes near freezing. Life becomes sparse, alien. Yet, even here in this seemingly barren wasteland, we haven't reached the ocean's true secrets. Beyond 6,000 meters lies the Hadal Zone, named after Hades, the Greek underworld. This isn't the vast plains of the abyssal. The Hadal Zone exists in fragments, a patchwork of deep trenches and troughs, carved by geological violence. These trenches cover an area roughly half the size of Australia, yet represent less than 1% of the seafloor. They're rare, they're isolated, and they're completely alien. Each trench forms where tectonic plates collide with such force that they tear the seafloor apart. Subduction zones create these scars in the Earth's crust, plunging 6 to 11 kilometers down into crushing darkness. Scientists call it aqua incognita, unknown waters. That's not poetic language, it's literal truth. The deepest of these scars lies in the Western Pacific. Challenger Deep, nestled within the southern Mariana Trench, holds the current record. Modern pressure-derived measurements place it at 10,935 meters below mean sea level, with a margin of error of just 6 meters. That precision comes from 2020 submersible transects using gravity and water level corrections that weren't possible just decades ago. But here's where things get strange. Different studies report different depths for Challenger Deep. The numbers shift depending on the method used. Sonar versus pressure readings, sound speed profiles, GOED corrections, even tidal states. The 2021 pressure study notes that gravity correction alone can shift measurements by substantial amounts. The deepest point on Earth keeps moving on our maps. The trench itself defies simple navigation. 3 distinct basins run west to east along the trench axis: western, central, and eastern. Each plunges below 10,850 meters. They're separated by underwater ridges just a few hundred meters higher, creating a maze of narrow slots and steep walls. The deepest section measures roughly 11 kilometers long and just over 2 kilometers wide. For perspective, that's like trying to hit a target the size of a small city from space. The terrain actively fights human exploration. Steep walls channel and trap sediment. Earthquakes trigger slope failures that create turbidity currents. Underwater avalanches that can bury instruments or snap cables. The hydrography grows increasingly complex with depth. Recent studies reveal layered, deep circulation patterns and turbulent mixing that can shift equipment and distort acoustic signals. 3 basins exist, but only one likely holds the true deepest point. Current high-precision pressure measurements suggest the eastern basin wins, though the western basin falls within measurement uncertainty. The deepest point shifts not because the seafloor moves dramatically, but because our methods keep improving and our understanding keeps evolving. Even our best 12 kHz multi-beam sonar leaves massive footprints at an 11-kilometer depth. A single shallow ping can miss a nearby depression. Earthquakes reshape micro-relief. Mass wasting events bury old lows and expose new ones. The deepest point on our planet remains a moving target, hidden in trenches that exist like scattered wounds across the ocean floor, and we've barely begun to explore what lies down there. 10,935 meters. That's our current best answer for how deep Challenger Deep reaches. But that number comes with a caveat, plus or minus 6 meters with 95% confidence. For the deepest point on our planet, we can only narrow it down to a 12-meter range. That's like measuring the height of a 3-story building with uncertainty. The problem isn't our technology, it's physics itself. 2 methods dominate deep ocean measurement, and each fights different battles against the laws of nature. Ships use multi-beam echo-ounders, sophisticated sonar systems that send fans of acoustic beams toward the seafloor. The concept seems straightforward. Sound travels down, bounces back, and travel time equals depth. But 11 kilometers down, sound doesn't travel in straight lines. Water temperature changes with depth. Salinity shifts. Pressure increases. Each layer bends sound waves like a lens refracting light. These thermocline create what oceanographers call smile and frown artifacts. Systematic errors that can make the seafloor appear deeper or shallower than reality. Sound speed profiles must be measured constantly, sometimes every few hours in highly variable areas. Miss the local conditions and your depth measurement becomes fiction. The math grows complex quickly. Total propagated uncertainty, TPU in the trade, combines errors from sound speed profiling, GPS positioning, timing delays, ship motion, beam geometry, wave action, and data processing. Each error source multiplies through the calculation. At an 11-kilometer depth, tiny mistakes become major problems. Submersibles take a different approach. They carry high-accuracy pressure sensors down to the seafloor and use hydrostatic principles to calculate depth. Pressure equals the weight of water above, so measuring pressure should reveal depth directly. But converting pressure readings to geometric depth requires knowing the exact density of every water layer during the dive. Temperature affects density. Salinity affects density. The calculation demands precise temperature and salinity measurements throughout the descent. Then comes gravity. Earth's gravitational field isn't uniform. Ocean trenches sit in strong gravity anomalies where the sea floor has been pulled deep into the planet. Converting pressure to depth requires knowing the exact local gravitational acceleration. Use the wrong gravity model and your depth calculation shifts by meters. The 2021 study that produced our current 10,935 meters figure notes that gravity correction alone represents a substantial component of the final number. Reference surfaces complicate everything further. Depth. Relative to what? The ocean surface moves constantly with tides, waves, and atmospheric pressure. Mean sea level varies regionally due to Earth's irregular shape and gravitational field. The GeoWhite, our best model of mean sea level, requires complex calculations to determine local height. Different reference choices shift depth measurements by several meters. Even our instruments betray us at these extremes. Pressure sensors face calibration limits, thermal drift, and long-term stability issues. The 2021 analysis found that pressure sensor uncertainty dominated the error budget for their depth measurement. GPS and inertial navigation systems on surface ships accumulate position errors. Timing delays between the sonar pulse and the recording create systematic biases. Processing software makes assumptions about sound propagation that may not hold in complex deep water conditions. Resolution becomes another enemy. Low-frequency sonars needed for deep water penetration create large footprints at an 11-kilometer range. A single sonar beam might cover an area the size of a football field on the seafloor. Subtle depressions disappear within the beam pattern. Later surveys using different track lines or pressure transects discover slightly deeper points that earlier measurements missed entirely. The numbers shift not because the seafloor moves dramatically, but because our understanding improves incrementally. Ship sonars require perfect sound speed profiles through 11 kilometers of varying water. Submersibles need perfect pressure measurements and gravity models. Neither achieves perfection at full ocean depth. Weather adds another variable. Internal waves propagate through deep water, creating temporary changes in sound speed structure. Tidal flows alter water properties along submersible dive tracks. Storm systems thousands of kilometers away generate deep water waves that shift acoustic paths. The ocean itself conspires against precise measurement. Different expeditions report different depths for the same location because they use different methods, reference different surfaces, apply different gravity models, and face different environmental conditions. The deepest point on Earth becomes a moving target for our instruments, even when the seafloor remains perfectly still. 10,935 meters represents our best current estimate, derived from pressure-reference submersible transts with full gravity and GeoWhite corrections applied to mean sea level. The plus or minus 6 meters reflects honest uncertainty in a measurement that pushes both technology and physics to their limits. The ocean's deepest number isn't imprecise because we lack skill. It's imprecise because measuring the bottom of the world remains one of the hardest problems in geophysics. 11 kilometers of water weighs down with incomprehensible force. The rule of thumb says pressure rises roughly 1 atmosphere every 10 meters. At Challenger Deep's 10,935 meter floor, that creates about 1,100 bar over 16,000 pounds per square inch pressing against every surface. put that in perspective. Every square inch of a deep sea vehicle experiences the weight of a small car, pushing inward constantly from all directions. The implosion energy stored in that pressure differential could power a small city for minutes. When things fail at these depths, they don't just break, they vanish. The research vessel Nereus learned this lesson the hard way. In 2014, while exploring near 10,000 meters, something went catastrophically wrong. Recovery crews found only debris fragments. Analysis confirmed pressure-induced implosion. 11 kilometers down, failure happens faster than human perception. External pressure attacks materials in ways surface engineers rarely face. Steel and titanium don't simply yield like they would under tension. Instead, they buckle. Spherical and cylindrical shells develop local dents that grow exponentially. What starts as a microscopic imperfection becomes a catastrophic collapse zone in milliseconds. The mathematics of shell buckling under external pressure reveals uncomfortable truths. Tiny flaws load capacity dramatically. Seals face their own torture test. Elaster O-rings suffer compression set under sustained pressure and cold temperatures. The rubber literally forgets its original shape. Caling force drops. Water finds microscopic pathways through materials that seem perfectly sealed at the surface. Conservative engineers specify harder durometer elastomers, anti-extrusion backup rings, and oversized groove designs. Even then, many deep ocean systems abandon rubber entirely. When elastomers aren't enough, engineers turn to glass, to metal seals, and metal sea seals. These hermetic solutions eliminate the organic chemistry problems that plague rubber under extreme conditions. Glass bonds to metal at the molecular level. Metal seals deform plastically to fill surface irregularities. Both approaches trade simplicity for reliability at full ocean depth. The composite material revolution that transformed aerospace hasn't conquered deep ocean pressure. Carbon fiber excels in tension, but struggles under compression and cycling loads. The Titan submersible tragedy highlighted delamination and fatigue risks in experimental composite hulls. The Coast Guard's 2025 investigation called the implosion preventable, emphasizing the dangers of operating without third-party certification. Metallic spheres dominate full ocean depth applications for good reason. Hull geometry matters more than material strength. Titanium spheres represent the current gold standard for crewed deep ocean exploration. The limiting factor submersible uses a thick titanium alloy sphere certified for repeated dives to 11,000 meters. Precision, roundness and thickness control determine buckling margins. Machining tolerances approach 99.9% circularity, because tiny, out of roundness errors, pressure capacity. Spheres beat cylinders through simple physics. A sphere carries membrane stress uniformly across its surface. No longitudinal or hoop stress concentrations like cylinders experience. For equal material thickness, a sphere achieves roughly twice the strength of a cylinder under external pressure. Fewer weak axes mean fewer failure modes. Buoyancy systems face their own depth limitations. Syntactic foam resin mixed with hollow glass microspheres works reliably to about 6,000 meters. Beyond that depth, the microspheres begin crushing. Buoyancy drops permanently as the foam densifies under pressure. Full ocean depth systems abandon foam entirely. Glass and ceramic spheres replace foam at extreme depths. These solid buoyancy elements maintain their volume under crushing pressure. Engineers package them in protective frames and distribute them around vehicle hulls. Where syntactic foams surrender their lift, ceramic spheres keep working. Viewports shrink with depth for survival. Acrylic windows follow strict ASME pressure vessel standards that specify thickness to diameter ratios and inspection schedules. Conical or hemispherical profiles seat in compression against metal frames. Design reality forces engineers to choose between view and safety. Deeper means smaller, thicker windows to control edge stress and fatigue. Stress concentrations develop at the inner edges where acrylic meets metal. Generous transition radii and low friction seating become critical design elements. Many full ocean depth vehicles accept tiny viewports or eliminate them. Cameras live in separate pressure housings to avoid turning the crew sphere into a stress concentrator. The rule of spheres applies everywhere. Minimize penetrations. Hardman mount what you must and accept that every hole weakens the whole. Penetrations remain the enemy of deep ocean design. Every hatch, viewport, or electrical feed-through creates potential stress concentrations and sealed paths. Uncertified experimental holes under external pressure prove unforgiving. The Titan investigation transformed that lesson into policy through tragedy. At an 11-kilometer depth, the ocean tests every engineering assumption. Small defects become catastrophic problems. Materials behave differently under extreme external pressure than they do in normal applications. Success requires abandoning surface intuitions and embracing the harsh reality that deep ocean engineering operates by different rules entirely. Water swallows radio waves like light disappears into a black hole. GPS signals penetrate seawater by mere centimeters before dying completely. The electromagnetic spectrum that connects our surface world becomes useless underwater. Submarines and deep sea vehicles must abandon everything we take for granted about instant communication and switch to acoustic links. Sound waves traveling through the ocean itself, but sound moves at just 1,500 meters per second through water. From Challenger Deep's floor to the surface ship, waiting 11 kilometers above, a single acoustic ping takes over 7 seconds to complete its round trip. Real-time conversation becomes impossible. Every exchange requires patience measured in geological timescales. The data rates paint a sobering picture. CHAI's micro-ohm, representing some of the most advanced underwater acoustic communication systems available, supports payload rates between 300 and 5,000 bits per user under typical conditions. That's slower than dial-up internet from the 1990s. Higher data rates exist, but they sacrifice range and robustness, exactly what you can't afford at full ocean depth. Sound doesn't travel in straight lines through the ocean. Water layers of different temperatures and salinities bend acoustic waves like atmospheric mirages. Bend light. Thermoclines create natural lenses that focus or defocus sound energy. The SOFAR channel, a deep sound speed minimum, acts like an underwater waveguide, trapping acoustic energy and refracting it toward the speed minimum. Signals that should travel directly from the seafloor to the surface instead bounce and bend through the water columns, complex structure. Shadow zones form where refraction bends sound rays away from receivers. A submersible sitting in perfect line of sight to the surface. Ship might exist in an acoustic dead zone created by temperature layers hundreds of meters above. Communication becomes a matter of geometry, thermodynamics, and luck. Trench walls amplify these problems exponentially. Steep terrain creates multipath propagation, where acoustic signals bounce off underwater cliffs and arrive at receivers multiple times with different delays. Packets collide with their own echoes. Data arrives corrupted or out of sequence. The narrow geometry of trenches, like Challenger Deep, turns communication into an echo chamber of interference. Ambient noise steals bandwidth from every transmission. Storm waves generate broadband acoustic energy that penetrates deep water. Ship traffic creates a constant low-frequency rumble. Seismic activity along trench walls adds unpredictable noise bursts that can completely mask communication attempts. The ocean itself becomes an active opponent to information transfer. Ultra-short baseline navigation systems offer the best available underwater positioning, but they struggle against the same physics that defeat communication. USBL works by measuring range and bearing from a surface vessel to a sub-EC transponder. Sonodyne's Ranger 2 system claims accuracy up to 0.04%, 0.04% of slant range and tracking capability to 11,000 meters under favorable conditions. Geometry betrays precision at extreme depth. The mathematical relationship between baseline length and angular accuracy means that very long slant ranges combined with relatively small surface arrays create large positional errors. A few meters of uncertainty at the surface array translates to tens of meters of uncertainty at the seafloor. Refraction corrupts every range and bearing measurement. Sound waves traveling through varying water layers don't follow the straight-line paths that navigation algorithms assume. Wrong sound speed profiles, bias distance measurements. Bearing calculations shift as acoustic paths bend through thermoclines. The same temperature and salinity variations that create communication shadow zones also systematically distort position fixes. Surface vessel motion adds another layer of complexity. Pitch, roll, and heave move the acoustic transducers constantly. Sensor offsets between navigation arrays and vessel reference points introduce timing errors. Dynamic positioning systems work to maintain station, but wave action and current create continuous motion that degrades acoustic tracking accuracy. Trench walls block line of sight paths and create false acoustic returns. Sound waves reflect off underwater cliffs and arrive at receivers through indirect paths that confuse ranging calculations. The narrow confines of trenches limit geometric diversity. The multiple bearing angles that robust positioning requires. The result is a systematic communication breakdown at full ocean depth. Mission planners don't just expect silence, they design for it. Autonomous underwater vehicles carry pre-programmed mission plans because real-time control becomes impractical when every command exchange requires multiple seconds and might fail. Even status updates become sparse. Delayed transmissions measured in minutes rather than seconds. At 11 kilometers down, we communicate in chirps rather than conversations. Navigation becomes estimated, plus occasional pings rather than continuous GPS tracking. The electromagnetic tether that connects our surface worlds snaps completely underwater, leaving exploration vehicles to operate in communication darkness that would terrify surface navigators. The deepest places don't just challenge our engineering, they cut the conversation. January 23rd, 1960, Navy Lieutenant Don Walsh and Swiss oceanographer Jacques Picard climb into Trieste. A massive bath scarf filled with gasoline for buoyancy and weighted with iron pellets. They descend through crushing darkness for nearly 5 hours until they touch the deepest known point on Earth. 2 men become the first humans to witness Challenger Deep firsthand. Then silence. 52 years of silence. In March 2012, filmmaker James Cameron made the next solo descent in Deep Sea Challenger, reaching about 10,980 meters. The gap between crewed visits to the deepest place on our planet spans longer than the entire space age. More time passed between human visits to Challenger Deep than between the Wright brothers' first flight and the moon landing. Only in the last few years has repeatable huddle diving become reality. The DSV limiting factor began systematic full ocean depth operations in 2019, completing dozens of Hadal dives across all 5 oceans through the 5 Deeps and Ring of Fire expeditions. Multiple visits to different Challenger Deep basins proved that deep ocean exploration could become routine rather than heroic. China's Fendua submersible joined the exclusive club in 2020, carrying 3 crew members to about 10.99 meters in a titanium sphere designed for repeated operations. Multiple Hadal sorties that year showed another nation's commitment to deep ocean capability. the numbers remain staggeringly small. Credible public tallies show about 27 people have visited Challenger Deep as of 2022. Dawn Wright became the 27th documented visitor during a 2022 dive aboard Limiting Factor. The entire club of humans who have witnessed the deepest place on Earth fits comfortably in a single classroom. Compare that to space travel. By the mid-2020s, over 600 people will have crossed into space using the international definition of 100 kilometers altitude. Some sources count over 700 using the United States 50-mile definition. Space tourism companies now launch dozens of passengers per year on suborbital flights that last minutes rather than the full day required for a hard-hull expedition. The scarcity of deep ocean visitors isn't accidental. It reflects fundamental barriers that spaceflight has largely overcome. Certified full ocean depth submarines barely exist. Only a handful of class-repeatable crewed vehicles can reach Hadal depth safely. Triton's 36,002 limiting factor earned DMV certification for routine operations to 11,000 meters. Fendu represents China's three-seat titanium sphere capability. Legacy craft like Trieste and Deep Sea Challenger served single programs and retired after proving concepts rather than enabling sustained exploration. Ship time costs astronomical sums and remains scarce. Large research vessels bill at daily rates measured in tens of thousands of dollars. NSF documentation shows about $30,000 per day for regional class vessels with specialized deep ocean support ships commanding premium rates. A single Hadal expedition burns weeks of ship time at five-figure daily costs plus submersible operations, crew and equipment. Weather windows close without warning. The western North Pacific lacks predictable seasonal patterns, though typhoon activity typically peaks between September and November around Micronesia. Storm systems can shut down operations for weeks, burning expensive ship time while crews wait for diving conditions. International permits create bureaucratic nightmares. Marine scientific research within exclusive economic zones requires coastal state consent under international law. Paperwork and diplomatic notices can exceed available cruise windows. Challenger Deep sits within the Federated States of Micronesia's waters, adding another layer of coordination to every expedition. Operational risks multiply at full ocean depth. Diving requires specialized support ships, trained teams, heavy lift cranes, autonomous landers, long baseline acoustic beacons, and extensive spare parts inventories. Weather delays, winch failures, buoyancy system problems, or battery faults can scrub dive operations entirely. Each system's failure cascades through complex support chains that space missions avoid through vertical integration. Capital costs reach staggering levels. The limiting factor system reportedly cost $37 million for the submersible alone, within a private program measured in multiple tens of millions of total investment. Building Hadal capability requires sustained funding commitments that exceed most scientific budgets. The permitting typhoons and ship scheduling gatekeepers had science as effectively as crushing pressure. Space launches happen on predictable schedules from controlled facilities. Deep ocean expeditions depend on weather, international cooperation, and vessel availability that can shift without notice. It's easier to send tourists to space than scientists to the Hadal floor. Suborbital space flights now scale to commercial operations with multiple passengers per mission. Hadal exploration remains limited to single-digit crew sizes on expeditions that might launch once per year if conditions align. Trieste opened the door in 1960. 52 years later, Cameron proved the depths remained accessible. Only now, with limiting factor and Fendus, has visiting the deepest place on our planet become anything approaching routine. The club remains tiny by design, not heroism, but physics, logistics, and economics. Money falls into the deep ocean faster than submersibles. Woods Hole. Oceanographic Institution states that operating costs for Alvin dives, including support from research vessel Atlantis, run about $45,000 per day. That's for reaching 6,500 meters. Impressive depths that still fall far short of full ocean depth. Had operations cost significantly more, a day in deep ocean billing doesn't follow calendar logic. Research institutions charge by operating day multiplied by the daily rate. And weather standby days often count as charge days whether you dive or not. Storms can trap expensive research vessels on station for weeks while daily charges accumulate. Time becomes the enemy of budgets, just as pressure becomes the enemy of equipment. Mobilization costs multiply beyond the basic day rate. Crane hires, port logistics, and specialized preparation get charged separately to science parties. Remote locations like the Western Pacific inflate these costs dramatically. Challenger Deep sits within the Federated States of Micronesia, requiring long transits, fuel, customs clearance, and diplomatic coordination that coastal research avoids entirely. Ship class determines the baseline expense. National Academies reviews show that ocean-class global research vessels average in the tens of thousands of dollars per day before adding any vehicles or scientific payloads. The ships capable of supporting full ocean depth operations represent the most expensive tier of research infrastructure. The full technology stack for deep work creates cascading costs. Dynamic positioning research ships require specialized A-frame cranes and winch systems. Submersibles need launch and recovery platforms. Acoustic positioning demands long baseline transponder networks. Scientific measurements require CTD sensors, acoustic Doppler current profilers, and comprehensive spare parts inventories. Each component demands specialized technicians who understand systems integration at the bleeding edge of marine technology. Full ocean depth operations occupy their own cost category entirely. The Triton 36002 limiting factor carries DMV classification for repeatable dives to 11,000 meters. Certification achieved through multiple witnessed full ocean depth tests. Classification imposes design reviews, materials traceability, proof testing, and inspection regimes that multiply development time and costs. Few marine systems face such stringent certification requirements. Custom metallurgy and precision machining drive costs beyond typical marine hardware. Limiting factor's crew sphere uses about 90 millimeters thick titanium alloy, requiring precision forging and extremely tight roundness tolerances. Few vendors worldwide can manufacture pressure hulls to these specifications at any price. The specialized supply chain creates bottlenecks and premium pricing for every component. Specialized sensors for hadal mapping remain rare and expensive. The pressure drop platform carried one of the few sonar systems capable of mapping to full ocean depth, a capability that requires both hardware and operational expertise available nowhere else in the commercial market. Even basic scientific instrumentation faces custom engineering for extreme pressure environments. Capital costs reach staggering scales before any operations begin. Public reporting places limiting factors construction around $37 million for the submersible alone. The complete hadal exploration system, ship, submersible and landers was marketed as a $50 million package. These figures underscore the cost here that full ocean depth capability demands before charging a single day rate. Geographic logistics impose additional penalties. Challenger Deep's location in the remote Western Pacific requires extensive transits, fuel planning, and port clearance logistics that inflate costs compared to coastal research cruises. Every aspect of hadal exploration happens far from infrastructure, supply chains, and emergency support that other marine science takes for granted. Failure costs multiply catastrophically in deep ocean work. Woods Hole's hybrid remotely operated vehicle Neos, built for about $8 million, suffered pressure-induced implosion at 9,900 meters in 2014. The loss created immediate multi-million-dollar write-offs, plus lost cruise time for programs that had planned years around the vehicle's capabilities. Japan's Kaiko provided another expensive lesson in 2003 when its secondary cable snapped during recovery operations amid typhoon conditions. The entire vehicle vanished into the deep ocean, representing not just the loss of hardware, but years of development investment and scheduled science programs. Weather and recovery loads can destroy deep ocean assets faster than pressure failures. Knock-on costs from equipment losses extend far beyond replacement values. Programs absorb additional ship days for search and recovery operations, emergency demobilization, re-engineering efforts, and multi-year replacement cycles. Grant funding clocks continue ticking while capabilities remain offline. The ripple effects of a single equipment failure can derail research programs for years. The mathematics become sobering quickly. $45,000 per day gets you Alvin operations to 6,500 meters with full ship support. Full ocean depth campaigns stack costs on top of that baseline. Class submersibles, specialized sonar systems, additional technicians, longer transits, and premium logistics. The rarer the hardware, the stricter the certification requirements, and the fewer the vendors, the higher the costs climb. When equipment fails at 11-kilometer depth, total write-off becomes the norm rather than the exception. The budget shock rivals the pressure shock. Deep ocean exploration doesn't just push the boundaries of engineering. It pushes the boundaries of institutional funding to breaking points that few research programs can sustain. As of World Hydrography Day in June 2025, only 27.3% of the global seafloor has been mapped to modern standards using ship-based sonar systems. The remaining 72.7% relies on satellite-derived gravity maps and sparse depth soundings, a patchwork of data that can miss entire mountain ranges hidden beneath the waves. Modern standards mean multi-beam sonar systems that paint detailed acoustic pictures of the seafloor. Everything else depends on satellite alimimetry that measures subtle variations in Earth's gravitational field caused by underwater topography. These gravity-based maps excel at revealing large features like mid-ocean ridges and seamounts, but they resolve details at kilometer scales rather than the meter-scale precision that had exploration demands. The fundamental resolution problem becomes stark at full ocean depth. Only low-frequency sonar systems like the Kongsberg EM-124 can reach 11,000 meters with workable acoustic coverage. At that depth, a one-dairy sonar beam spreads to roughly 190 meters across at the seafloor directly beneath the ship. Outer beams grow even larger due to grazing angles and acoustic spreading. Small features, the narrow slots and micro depressions that might hold the deepest points, vanish into these acoustic footprints. Swath coverage trades detail for efficiency. The EM-124 can map swaths 30 to 40 kilometers wide in deep water, allowing rapid reconnaissance of vast areas. But outer swath soundings suffer from larger footprints, increased refraction sensitivity, and lower signal-to-noise ratios. The data becomes perfect for regional mapping, but inadequate for finding the exact deepest pixel within a trench system. Sound doesn't travel in straight lines through the ocean's layered structure. Thermoclines and salinity variations bend acoustic beams like atmospheric mirages bend light. Without frequent sound speed profile measurements and careful ray tracing corrections, sonar returns shift systematically from their true positions. The same physics that creates communication problems also corrupts barometric mapping at the scales that matter for hadal targeting. Even the latest generation full ocean depth surveys acknowledge uncertainty. Studies publishing the deepest points of each ocean note that methodological and processing choices affect final depth measurements by several meters. The maps that guide expensive Hadal expeditions carry inherent uncertainties that can misdirect entire research programs. Satellite allometry offers global coverage, but fundamentally cannot substitute for ship-based sonar at all scales. Gravity field mapping typically resolves features at 5 to 10 kilometer scales in classical applications, with best-case claims reaching 1 to 4 kilometers under ideal conditions. That resolution remains far too coarse for pinpointing local depth maxima within narrow trench systems, where the deepest points might be separated by hundreds of meters rather than kilometers. The consequences play out in expensive dive time lost to basic navigation. Coarse barometric data or outer swath sonar coverage can place the pre-dive deepest spot hundreds of meters from its true location. First dives become search transects instead of productive science operations. Precious ship days and submersible operations burn through target acquisition rather than advancing scientific understanding. Trench topography actively fights mapping efforts. Steep walls create grazing angle gaps and acoustic multiath that leave data shadows exactly where the seafloor drops toward maximum depth. Crews routinely return to remap areas at tighter line spacing and slower vessel speeds, consuming additional ship time before any landers or submersibles can begin their primary missions. Technical constraints multiply at extreme depth. Ping rates slow as acoustic travel times stretch to multiple seconds for each sounding. Along track footprints expand with vessel speed, forcing slow surveys to maintain adequate seafloor sampling. Fine Kale features require dense line spacing that can consume entire research cruises before any deep water assets deploy. The mathematics becomes brutal. At 10 to 11 kilometers depths, acoustic systems operate at their absolute limits. Beam geometry, refraction effects, and footprint sizes all work against the precision that Hadal science demands. Processing choices that seem minor in shallow water, ray tracing algorithms, beam selection criteria, uncertainty models determine whether expensive deep water operations succeed or fail. Until more seafloor receives modern ship sonar coverage, Hadal expeditions must budget entire dives for relocating slopes, identifying sills, and finding the true local depth minimum before cameras and samplers can begin meaningful work. Navigation uncertainty consumes time, fuel, and funding that research programs can barely afford. The irony cuts deep. We possess detailed maps of Mars, Venus, and the lunar surface created by orbital reconnaissance missions. Yet, the deepest places on our own planet remain poorly charted territories where expensive scientific expeditions begin with basic questions about where to point their cameras. The seafloor mapping gap doesn't just represent incomplete knowledge. It actively wastes the scarce resources that deep ocean science requires for advancement. We've mapped more of the moon's surface than our ocean floors, and the cost shows in every misdirected dive to the Hadal depths. July 2015, the US Coast Guard cutter Sequoia deploys something unprecedented into Challenger Deep, a hydrophone mowing designed to record ambient sound at the deepest known point on Earth. For 23 days, this acoustic sensor sits on the seafloor, 36,000 feet below the surface, listening to whatever sounds might penetrate to the bottom of the world. Scientists expected to find one of the quietest places on our planet. 7 miles of water should muffle most noise, creating a zone of acoustic isolation where only the subtle sounds of deep ocean currents and rare geological events would register. The recordings tell a completely different story. The deepest place on Earth buzzes with constant noise. Robert Gack, NOAA research oceanographer and chief project scientist, summarized the surprise. You would think that the deepest part of the ocean would be one of the quietest places on Earth. Yet there is almost constant noise. The acoustic environment at Challenger Deep reveals a seafloor that hears the entire world above. Earthquakes dominate the soundscape. the ambient sound field is dominated by the sound of earthquakes, both near and far, creating a continuous background of seismic rumbling that propagates through solid rock faster than through water. Tectonic activity thousands of miles away registers clearly on the deep ocean hydrophone, turning the seafloor into a global seismometer that captures Earth's geological breathing. Marine life adds its voice to the acoustic chorus. The distinct moans of bowline whales penetrate 11 kilometers of water column to reach the deepest ocean floor. Blue whales, humpback whales, fin whales, and minke whales all contribute to an underwater symphony that spans ocean basins. Their calls travel vast distances through the Sofa Channel before filtering down to the Hadal depths. Human noise reaches even these remote depths. The hydrophone also picked up sound from ship propellers and active sonar signals. Commercial shipping lanes thousands of miles above still generate acoustic signatures that penetrate to the deepest trenches. The cumulative effect of global maritime traffic creates a constant anthropogenic background hum that follows human activity patterns across the Pacific. Weather systems far overhead leave acoustic footprints on the abyssal floor. During the hydrophone deployment, a Category 4 typhoon that just happened to pass overhead registered clearly in the recordings. Storm waves breaking at the surface generate low-frequency pressure waves that propagate through the entire water column. The seafloor experiences weather as acoustic events rather than direct physical contact. The technical achievement behind these recordings reveals both the capabilities and limitations of deep ocean instrumentation. The hydrophone package recorded continuously in the 10 to 32,000 Hz range throughout its deployment, capturing broadband acoustic signatures across frequencies that span natural and anthropogenic sound sources. But retrieving the data required patience. Scientists had to wait until November to recover the instrument due to ship schedules and persistent typhoons in the Western Pacific. The contrast becomes striking when compared to communication challenges that plague deep ocean operations. Sound travels efficiently through the ocean's layered structure, carrying acoustic signatures from earthquakes, marine life, ships, and weather systems to the deepest seafloor. Yet, the same physics that allows passive sound reception makes active communication nearly impossible at all depths. Natural sound propagates through established acoustic channels without requiring power, precise timing, or complex protocols. The Sofa Channel guides low-frequency energy across ocean basins. Seismic waves travel through solid rock with minimal attenuation. Surface-generated noise follows pressure wave propagation that spans the entire water column depth. Active communication systems face entirely different physics. Acoustic modems must overcome multi-eth propagation, ambient noise interference, and geometric limitations that passive listening avoids. Two-way communication requires precise timing, error correction, and sufficient power to overcome channel losses that one-way natural sound transmission ignores. The hydrophone recordings establish a baseline for ambient noise in the deepest part of the Pacific Ocean, documenting acoustic pollution that reaches even the most remote marine environments. Human-generated noise has increased steadily over the past several decades, and the Challenger Deep recordings prove that no part of the ocean remains acoustically isolated from human activity. The irony cuts to the heart of deep ocean exploration challenges. The seafloor hears everything. Earthquakes from distant tectonic boundaries, whale songs from other ocean basins, ship propellers from surface shipping lanes, and storm systems passing far overhead. Yet, human efforts to establish two-way communication with instruments at these depths struggle against the same acoustic environment that efficiently carries natural and anthropogenic sounds to the deepest places on Earth. Sound travels, data doesn't easily. The deepest ocean floor eaves drops on the entire planet, while we struggle to exchange even simple status messages with our most advanced deep sea vehicles. Life reaches extraordinary depths, but physics ultimately wins. In 2023, researchers filmed a pseudo-Paris snailfish at 8,336 meters in the Izu-Asawara Trench, the deepest verified sighting of any vertebrate. Collections from the Japan Trench recovered specimens from 8,022 meters. These ghostly translucent fish represent vertebrate life pushed to its absolute physiological limit. No fish has ever been found deeper than roughly 8 to 200 meters. And the reason comes down to cellular chemistry. Fish pack their cells with trimethylamine oxide, TMAO, an osmolyte that stabilizes proteins under crushing pressure. But TMAO accumulation has limits. Mathematical models predict that around 8,200 meters, fish reach isosmotic par with seawater. Beyond that depth, cellular water balance fails catastrophically. The snailfish depth record matches these predictions almost perfectly. Hadal snailfish survive through chemistry rather than armor. They've abandoned the heavy mineralization that characterizes shallow water fish. Their skulls remain cartilaginous and soft. Their tissues contain TMAO concentrations that increase systematically with habitat depth. Specialized gut microbiomes help process the unique chemical environment of trench waters. These fish push biochemistry to its breaking point instead of building structural defenses against pressure. But vertebrates represent just one small branch of Hadal life. Microbes thrive in the deepest trenches, and many actually prefer extreme pressure conditions. True pozoials, organisms that require high pressure to function, have been isolated from Hadal environments since the 1980s. Recent work reveals active pressure adaptive metabolisms operating under in situ conditions, including specialized pathways for degrading phenolic compounds that would challenge surface microbes. Trench sediments host distinct microbial communities with higher cell abundances than adjacent abyssal plains. Each trench system develops its own unique microbial fingerprint, suggesting isolated evolution in these deep ocean islands. The microbiology of Hadal environments reveals ecosystems that don't just tolerate extreme conditions, they depend on them. Amphipods, small crustacean scavengers, dominate the visible fauna of Hadal trenches. But these seemingly pristine deep ocean environments carry disturbing evidence of surface contamination. Studies across 6 trenches reaching depths of 10.90 meters found microelastics and synthetic fibers in over 70% of scavenging amphipods. Nylon, polyethylene, PVC, and rayon fibers appear in the guts of animals living at Earth's deepest accessible points. The contamination extends beyond plastic debris. Flame retardants, UV stabilizers, and other industrial additives appear in amphipod tissues from Hadal depths. Mercury isotope analysis reveals that near-surface mercury pollution gets transported into trench food webs through mechanisms that remain poorly understood. At the bottom of the world, our synthetic materials become food. Some had species develop remarkable chemical defenses. Hondelia gigas amphipods coat their exoskeletons with aluminum hydroxide gel derived from sediment chemistry and gluconic acid metabolism. This homemade armor possibly protects calcium carbonate shell structures from dissolution under extreme pressure and corrosive conditions. Evolution finds solutions in the deepest places that surface biology never faces. Yet fundamental questions about Hadal ecosystems remain unanswered at the deepest depths. We know that trenches act as deep centers with elevated microbial activity compared to abyssal plains. But identifying which organisms process which compounds along trench axes remains poorly resolved. The microbial metabolisms operating in the deepest mud represent some of the least understood ecosystems on Earth. Carbon cycling in Hadal environments operates by different rules than surface systems. Tectonic events completely rewire the carbon supply. After the 2011 Tohoku earthquake and tsunami, over 1 ton of organic carbon were flushed into the Japan Trench in a single event. Multi-year records show that event-dominated burial patterns characterize Hadal basins rather than the steady-state processes that govern most marine environments. Food delivery to had floors appears fundamentally episodic. Long periods of famine get interrupted by massive influxes. Carcass falls from marine mammals. Sediment gravity flows, carrying surface-derived organic matter and debris from tectonic disturbances. The first documented Hadal foodal communities, including colonization of a dolphin carcass, were only recently studied. Hadal ecosystems operate on boom and bust cycles that challenge conventional ecological models. Bioturbation patterns at extreme depth remain mysterious. Micro-CT analysis of sediment cores from depths exceeding 7,500 meters reveals biogenic structures and colonization sequences in gravity flow deposits. But the rates, agents, and mixing depths at 10,000 to 11,000 meters stay poorly constrained. The deepest measurements reveal more microbial respiration, more organic matter burial, and more anthropogenic contamination than scientists expected. But at 10.35 meters, we still cannot map who eats what, when, or how the deepest ecosystems respond to the episodic disturbances that define Hadal environments. Life exists at the bottom, but under rules that surface, biology barely recognizes. The seafloor at Hadal depths doesn't stay still. Trenches form where oceanic crust bends downward into Earth's interior at subduction zones, creating terminal sinks that trap sediment, organic carbon, and pollutants in basins 6 to 11 kilometers deep. But these aren't passive collection points. They're dynamic systems where geology literally moves beneath scientific instruments. March 11th, 2011. The magnitude 9.0 Tohoku earthquake generated the most powerful seismic event in Japan's recorded history. The epicenter sits offshore directly above the Japan Trench, within minutes of the main shock. Massive underwater landslides trigger basin-scale turbidity currents that race down the continental slope toward the trench axis. The entire Hadal environment transforms in real time. Ocean bottom pressure recorders capture the chaos as it unfolds. One instrument records its own displacement nearly 1 kilometer across the seafloor. Not because it failed, but because the sediment beneath it liquefied and flowed down slope. Direct measurement proves that powerful mass-wasting events can physically relocate scientific equipment during the very phenomena they're designed to study. The underwater avalanches continue for months. 4 months after the earthquake, in situ video cameras reveal dense clouds of suspended sediment extending 30 to 50 meters above the seafloor. Dead megapora litter the trench floor. Persistent downslope currents continue driving sediment toward the deepest basins. The bottom boundary layer becomes a turbid river flowing through underwater canyons. Sediment cores from subsequent expeditions reveal the earthquake's signature preserved in the geological record. Fresh turbidite deposits blanket wide areas of the Japan Trench. The 2011 event joins a stratigraphic archive of past giant earthquakes recorded in repeated trench parallel event beds. Recent synthesis work mapped 77 distinct event beds across 600 kilometers of the Japan Trench, each representing a moment when seismic activity reset the entire Hadal environment. The 2011 tsunami and its aftershocks reworked continental shelf and slope sediments across the entire region. Fine and coarse material flushed from shallow water sources gets transported into the deepest ocean basins through sediment gravity flows that operate like underwater flash floods. Shelf-to-trench coupling means that surface events propagate through the entire depth range of marine environments. Post-earthquake monitoring reveals persistent changes to the deep water environment. Elevated bottom water turbidity continues for years as weak near-bottom currents redistribute fine sediment at velocities measured in centimetres per second. The deep ocean's recovery from major disturbance events operates on timescales that span decades rather than seasons. Trenches follow a general pattern of episodic reset, followed by gradual accumulation. Earthquakes and landslides catastrophically disturb the seafloor environment. Between these events, fine materials settle slowly to form the thick layered sediment archives that preserve the geological history of seismic activity. The deepest ocean basins alternate between violent disturbance and quiet accumulation. These dynamics create operational nightmares for deep-sea research. Thick nepheloid layers and fresh turbidity plumes erase visibility for cameras and laser systems. Even stationary vehicles can trigger sediment clouds when their thrusters interact with freshly deposited fine material. Brownout conditions persist for months after major seismic events, making visual surveys impossible across vast areas of trench systems. Navigation systems suffer systematic degradation in disturbed environments. Active downslope flows create multi-ath propagation that corrupts acoustic ranging. Steep relief generates geometric problems for ultra-short baseline positioning. Landers can be displaced hundreds of meters or more during extreme events. Long baseline transponder networks become useless when reference points migrate with flowing sediment. Asset loss becomes a routine operational risk. Fresh turbidites and mass-wasting events scour cables, topple moorings and end-tomb seafloor instrument packages. Recovery operations become risky or impossible when equipment gets buried under meters of fresh sediment. The 2011 Japan trench experience documented multiple cases of scientific instruments lost to geological processes rather than technical failures. Time taxes accumulate after every major disturbance. Research teams must remap target areas at slow speeds, with dense line spacing before deploying expensive deep-sea assets. Accurate bathymetry becomes obsolete when the seafloor reshapes itself during seismic events. Ship days burn while bottom boundary layers settle enough to allow meaningful scientific operations. Scientific interpretation faces signal versus noise problems in dynamic environments. Short sediment cores may miss key event layers that preserve the most important geological information. Carbon budget calculations require trench axis, transects, and multi-year sampling programs to separate earthquake-driven pulses from background particle flux. Understanding hadal environments demands accounting for catastrophic events that can dominate decades of gradual processes. In the hadal world, earthquakes push the reset button regularly. Turbidity in rivers switches on without warning. Layered deposits stack rapidly during brief intervals of intense activity. Maps become obsolete faster than instruments can update them. The deepest ocean operates under geological rules that surface environments rarely experience at such extreme scales. Deep ocean exploration depends on choosing the right platform for each mission. 4 distinct approaches dominate hadal research, each with fundamental trade-offs that determine success or failure before deployment begins. Human-occupied vehicles put scientists directly at depth for real-time observation and sampling. The DSV limiting factor represents the current state-of-the-art. A DMV-certified 2-person titanium sphere rated for repeatable dives to 11,000 meters. Only a handful of such vehicles exist globally, making HOV time more precious than space on the International Space Station. Teams want HOVS for human vision and judgment in complex terrain. Computers excel at following pre-programmed instructions, but deep ocean exploration constantly presents unexpected discoveries that require immediate decisions. A marine biologist inside a submersible can instantly recognize unusual fauna and redirect sampling efforts. That intuitive flexibility remains impossible to replicate with remote systems operating through 7-second communication delays. OV constraints reflect their specialized nature. Viewports shrink with depth to manage stress concentrations, limiting direct observation to tiny windows. Payload capacity stays minimal compared to large robotic systems. Mobilization requirements demand specialized support ships, certified pilots, and extensive safety protocols that inflate operational costs and dueling complexity. Remotely operated vehicles offer real-time control through power and data tethers that connect surface operators to sophisticated underwater robots. The two-body JSON system exemplifies the approach. An armored 0.6 8-inch cable from the ship to the media shock-absorbing platform, then a 70-meter, neutrally buoyant tether to the working vehicle. This configuration reaches 6,500 meters reliably. Full OSEPth tethering becomes brutally difficult. 10 to 11 kilometers of heavy electro-optic umbilical creates massive drag forces and fatigue cycles that challenge even the strongest materials. Japan's KAO ROV proved this limitation catastrophically in 2003 when its secondary cable snapped during recovery operations. Post-failure analysis traced the break to aramid fiber fatigue at the cable termination under pressure cycling. ROVs excel where tether management remains practical. Depths up to 6,500 meters, where precision manipulation matters most. Beyond that range, the tether becomes the system's weakest component rather than its greatest strength. Autonomous underwater vehicles eliminate tether constraints by operating as programmable, untethered robots designed for wide area mapping and imaging. Without cable drag, AUVS can follow efficient survey lines and maintain long bottom times that tethered systems cannot match. WHI's Sentry platform exemplifies the autonomous approach with systematic mapping capabilities that span ocean basins. Communication reality limits AUV flexibility. Underwater acoustic modems achieve data rates between 80 and 5,400 bits per second, slower than the 1990s dial-up internet. Retasking autonomous vehicles requires sparse acoustic messages. That may take multiple attempts to transmit successfully. Real-time control becomes impractical when every command exchange spans multiple seconds with high failure rates. Navigation depends on inertial guidance systems, aided by Doppler velocity logs with periodic fixes from ultra-short baseline or long baseline acoustic positioning. Inertial drift accumulates between position updates, creating uncertainty that grows with mission duration and distance from acoustic reference points. UHI's hybrid N-IUS vehicle attempted to combine autonomous survey capability with fiber optic ROV control for precision work at full ocean depth. The system showed the concept successfully before suffering pressure-induced implosion in 2014, illustrating both the potential and risks of advanced deep ocean robotics. Landers represent the simplest and most robust approach to HADL research. Freefall frames carry cameras and samplers to the seafloor, operate autonomously during program deployments, then drop ballast weights to return to the surface for recovery. The approach works reliably at full ocean depth with relatively straightforward logistics. Number. AA notes that most had-depth seawater sampling relies on autonomous landers because costs and risks at extreme depths favor simple expendable platforms over complex tethered or human-occupied systems. Lander deployments can be repeated hundreds of times to build statistical datasets impossible with more expensive platforms. Lander limitations reflect their simplicity. Each deployment provides single location data without the spatial coverage of mapping systems or the precision manipulation capabilities of piloted vehicles. Recovery failures due to weather, surface drift, or acoustic beacon problems can result in total mission loss. Platform selection depends on mission objectives and acceptable risk levels. Unknown seafloor requires AUV mapping to establish targets and hazards before expensive assets deploy. Precision sampling and manipulation demand ROV capabilities where tether management remains practical. Human judgment in complex terrain justifies HOV deployment despite scarcity and cost. Long-duration monitoring and statistical sampling favor lander systems that accept single-point limitations. The decision matrix changes by the hour during actual expeditions. A UV to find targets, HOV or ROV to understand and sample discoveries. Landers to monitor breathing patterns over extended periods. Each platform excels within specific operational envelopes, but none provides universal capability for Hadal exploration challenges. When you're building something that's going to face pressures that could crush a car like a soda can, the difference between it should work and it will work becomes a matter of life and death. Material fatigue isn't just some engineering buzzword you throw around in textbooks. It's the slow, invisible killer that happens when metals get stressed over and over again. Microscopic cracks spreading like spider webs through what looks like perfectly solid steel. Every dive cycle puts stress on every bolt, every weld, every seal. The ocean doesn't care about your schedule or your budget. It's going to test every single weakness in your design, and if you haven't tested it first, the ocean will be the final exam you can't retake. This is why legitimate deep-sea operations follow inspection regimes that would make airline mechanics look casual. We're talking about X-ray inspections, pressure testing that goes beyond operational limits, and material analysis that tracks the molecular structure of every critical component. These aren't suggestions. They're the difference between coming back to the surface and becoming another cautionary tale that gets whispered about in engineering conferences. The test cycles alone would bankrupt most operations before they ever got wet. You don't just build a pressure vessel and hope it works. You build it, test it to destruction, analyze the failure, redesign it, and repeat this process until you understand exactly how and when it will fail under real conditions. The legitimate deep-sea vehicles that have successfully reached Hadal depths went through years of testing cycles. They tested components individually, then in assemblies, then the complete vehicle over and over again. Every gasket gets tested hundreds of times. Every viewing port is subjected to pressures that exceed operational requirements by massive margins. You test until you're certain of your margins, and then you add more margins on top of those margins, because the deep ocean has a way of finding problems you never imagined. Then came June 2023, and everything changed. The Titan submersible imploded at just 3,800 meters down, which isn't even close to Hadal's own depths. We're talking about less than half the depth of Challenger Deep, and 5 people died instantly when their pressure vessel failed catastrophically. The vessel was not certified as seaworthy by any regulatory agency or third-party organization, and this wasn't some oversight or bureaucratic delay. This was a deliberate decision to bypass the safety systems that every legitimate deep-sea operation considers essential. The Coast Guard investigation that followed painted a picture that should terrify anyone who thinks shortcuts are acceptable when lives are on the line. OceanGate consistently sidestepped safety concerns in a bid to maximize profits with operational and safety practices described as critically flawed. Their dive safety manual contained just 4 pages of procedures for operations that should require hundreds of pages of detailed protocols. What makes this tragedy even more significant is that it happened at depths that are routinely reached by properly certified submersibles. Military submarines operate at these depths. Research vessels make dives to the Titanic wreck site regularly. This wasn't pushing the boundaries of human knowledge into unexplored territory. This was a failure to follow established safety protocols for well-understood operations. The implosion reset public perception about submersible safety because it showed that even at relatively shallow depths, by deep ocean standards, the margins for error are absolute zero. The catastrophic implosion could have been prevented with investigators calling the vessel's safety culture and operational practices critically flawed. When your pressure vessel fails at 3,800 meters, it raises serious questions about whether current technology can safely reach the deepest parts of the ocean at all. This is the brutal reality of deep ocean exploration. The forces of destruction scale exponentially with depth. But human engineering capabilities don't scale at the same rate. Every additional 1,000 meters of depth doesn't just add more pressure. It multiplies the engineering challenges by factors that push even our best technology to its absolute limits. The certification processes that seem excessive and bureaucratic at the surface, pressures become literally life or death necessities when you're operating in environments where a single seal failure means instant death for everyone aboard. The ocean is unforgiving in ways that don't allow for second chances, learning from mistakes, or gradual improvements. You either get it right the first time, or the physics of extreme pressure makes sure there isn't a second time. This is why only a handful of people have ever reached the deepest parts of our planet, and why every single successful deep ocean mission represents not just technological achievement, but a victory over some of the most hostile conditions in the known universe. The ocean has this cruel trick where it gives you just enough hope that communication might work, then reminds you why you're completely alone down there. The SOFAR channel sounds like a miracle when you first learn about it. SOFAR, or Sound Fixing and Ranging Channel, is a naturally occurring ocean channel that allows sound to carry great distances. Scientists discovered that there's a sweet spot in the ocean, usually around 1,000 meters deep, where temperature and pressure create the perfect conditions for sound to travel thousands of miles without losing much energy. In the SOFAR channel, low frequencies in particular are refracted back into the duct. So the energy loss is small and the sound travels thousands of miles. Submarines during World War II figured this out and started using it to communicate across entire ocean basins. Whales have been using it for millions of years, calling to each other across distances that would span entire countries. The physics makes perfect sense. A sound wave traveling through a thermocline, a region of rapid change in temperature with depth, tends to bend downward as the speed of sound decreases with decreasing water temperature, but then is refracted back upward. As the speed of sound increases with increasing depth and pressure, the sound waves get trapped in this natural waveguide, bouncing up and down like they're trapped in an invisible tube that stretches across the ocean floor. But here's where the cruel joke comes in. The SOFAR channel is incredible for listening, absolutely useless for command and control. If a sound is generated by a point source in the SOFAR zone, it becomes trapped by refraction.